All right, well, we've got just 35 minutes to review as much as we possibly can for the exam, or in your case, for possibly classes you may take in college. So one of the most important things, obviously, we talked about this entire school year was actually right at the beginning. It was solving right triangles. We did it all through physics. We've done it off and on even here. And when we solve right triangles, remember we said if we know two sides of a right triangle, we can find the third side using Pythagorean theorem. If we know an angle and we know a side, we can use the angle and the side and sine, cosine, or tangent to solve for the missing side. For instance, we know sine is opposite over hypotenuse, cosine and tangent. All right, so for instance, let's suppose we had a triangle. And suppose we knew it was a right triangle, angle C at a right angle. Suppose we knew angle B up here is a 41-degree angle. Suppose we have this angle A here. And I know that this side, AC, is 6.37 inches. Well, to solve a right triangle, that means to find the other pieces and parts. So we know angle C is 90, we know angle B is 41. Obviously, we need to find
side C.
Okay, side little c, or AB, and we need to find angle A. Normally, that's what we would find first, is the missing angle if we've got two of the three. And of course, we also need
side A.
Side little a, or side BC. All right, so the first thing we solve is angle A. And remember, in a right triangle, the two acute angles are complementary. So if I know B is 41, A must be 49 degrees. And then we're not going to use that, remember, just in case we somehow screw up. We said 59 because, we're careless, whatever. But going off the given angle and the one given side, I could find, for instance, another side. What trig ratio would I need here, class? Sine. I know the opposite and I need the hypotenuse. So we would say that the sine of 41 degrees is equal to
6.37 over sine.
There we go. And then to solve for C, since it's in a denominator, we need to alternate and divide, right? We'll switch these two and say that C equals the 6.37 over the sine of 41 degrees. And what do we end up with? It would help for me to have my calculator here. End up with what for our answer? Making sure we're in degree mode, not radian mode, class.
Approximately 9.71.
What video thing? Just tell her to give the quiz and I will re-record it for her later. Just give the quiz. Okay. What did you get for your answer? I'm sorry?
Approximately 9.71.
All right. What's a good way to check? Because I was trying to do multiple things there and I didn't get it at all. What would be a good way for me to check that answer?
Your hypotenuse should be bigger than any one side, but smaller than the other two sides added.
Right. So far, does it seem right?
Yes.
Yeah, it's bigger than this side. So that feels okay. We'll really know more when we get to side BC or side A. Again, I'm not going to use Pythagorean theorem, though I could, perhaps, if I were really sure I had the right answer. But safest thing would be to find side A through other means. In this case, using the cosine. Ooh, no.
Tangent?
Cosine would still require the hypotenuse, which we said we just calculated. The tangent, right? We would say that the...
No, tangent of 41 equals 6.37 over 8.
There we go. And once again, we're going to have to alternate and divide. And this time we get what for our answer?
7.33.
It's 7.33 inches. Notice the hypotenuse is still bigger, but it's less than the sum of the other two sides. It makes me reasonably sure that my answer is correct. All right, questions on this? Let's suppose we had a right triangle, something like this, for instance. We'll call it A, B, C. So we've got the right angle C. Suppose we know that the hypotenuse is 5.15 feet. Suppose we know that down here we have 2.80 feet. And what would I need to solve for in this problem?
Side A, angle B, and angle A.
Right, side A or side BC, angle A and angle B. Which should I solve for first this time?
Side A.
Yeah.
I should get the missing side first, shouldn't I? Since I have the other sides. How do I find the side?
Pythagorean.
Well, this time both sides were given, not calculated, so Pythagorean theorem certainly would be the way to go here.
4.32.
Okay, and so we'll round it off and say 4.32 feet. All right, so far so good. All right, now as far as the angles, again, I don't want to use this value just in case I was wrong. By the way, a common mistake would be getting something like 16 or 17 if we're just forgetting to take a square root. And you're like, wait, that can't be right. That's way too big, right? It's got to be smaller than 5, and collectively, they need to be greater than the 5. How would I solve, for instance, then, if I'm not using this calculated value, how would I solve for angle A, Jamie?
You would have A over sine of A, B over sine of B.
I mean, I could technically use the law of sines, I guess. There's a much quicker, easier way, though.
Cosine.
Right, just use the cosine. I know the adjacent, I know the hypotenuse, so we'd say that the...
Sine
Go
over
ahead.
cosine of angle A is equal to 2.8 over 5.1.
There we go. We'll say the cosine equals adjacent over hypotenuse, but to solve for the A, I have to get rid of the cosine. How do I do that?
Arc.
Cosine.
Arc cosine on both sides, though we'll only show it on the other here. We showed it by canceling there. And what do we get for the measure of angle A?
57.
57.1.
Right, about 57.1 degrees. Again, we didn't have anything else to base angles off of, so we'll just go with the 3 sig figs we had before. And then for angle B, again, the temptation would be, I'll just subtract from 90, but what if I somehow even used the wrong function or something? I lose my ability to check. So what should I do now to solve for angle B, Quentin?
Take the arc sine of 2.0 over 500, or 5.15.
Good. Opposite hypotenuse, we'll take the arc sine of the 2.8 over the 5.15. And we get
32.9 degrees.
about 32.9 degrees. And now I have the ability to check and make sure they add up to 90. They do. I feel really confident about my answer going forward. Any questions at all on right triangles? Now, Jamie, a moment ago, was trying to use the law of sines. Jamie, we use the law of sines usually, not for right triangles, but for non-right triangles. What do you call non-right triangles, class? Oblique triangles, all right? So, for instance, maybe I gave you a triangle here, and we'll call this ABC. But this time we don't know that we have a right angle. Instead, I know that angle B is a 35-degree angle. I know that this side here is 17.5 centimeters, and this side here is 15.0 centimeters. Well, to solve, I need to get all the missing things. In this case, that would be
Side AC.
side AC, which we could call side B.
Angle A. And angle C.
And when it's a non-right triangle, I might use the law of sines, Jamie, or I might use the law of cosines. It all comes down to what arrangement do I have? What configuration of sides and angles do I have? Well, in this case, what do I have, class?
Side angle side.
Side angle side. For a side angle side triangle, is it sines or cosines?
Sine. No.
Well, one thing we could do is memorize that it's the law of cosines. Another way would be to try the law of sines. I mean, when in doubt, it's an easy formula, right? So we say, well, A is 17.5 over the sine of A equals B over the sine of 35 equals C over the sine of C. And you're like, well, now what? So the fact that you can't do anything with it, well, I guess it must be the law of cosines then. What is the law of cosines? It looks a lot like the Pythagorean theorem at the start.
C squared equals.
A squared minus.
It literally starts with the Pythagorean theorem. C squared equals A squared plus B squared, but then
Arc cosine.
minus Ooh, all right, write this in your notes. Make sure you got this in your notes. C squared equals a squared plus b squared minus 2ab times the cosine of c. C squared equals a squared plus b squared minus 2ab times the cosine of c. Now in this case, I don't want to actually solve for c squared. I want it to be b squared. How can I rewrite this so instead it says b squared equals?
A squared plus c squared minus 2ac cosine of b.
There we go. Just swap out all the b's and c's with each other, and we got the same exact formula. Obviously, we're going to want to take the square root at the end. Also remember, parentheses around this, and we'll do a little equals before hitting that square root. So let's find side b given sides a and c. And how long is side b? 10.059, blah, blah, blah. We want to put that in the memory of the calculator, remember. Because whenever you use, and we'll put centimeters on there, whenever you use the law of cosines to find a side, that first side needs to go in the memory. We're good to go on that? All right, once we've got it, now I could, if I wanted to, I could go back to the law of sines, or I use the law of cosines. I feel like the law of cosines might be a little bit quicker to find angle A. We kind of just reimagine this a little bit, and since we're finding an angle class, we're going to start by taking the arc cosine of something. In this case, it's the arc cosine of
b squared plus c squared minus a squared all over.
There we go. Angle A is going to be the arc cosine of b squared plus c squared minus a squared all over 2bc. Remember, b is the memory, so we're going to start with that memory squared plus c squared, which is the 15, minus the a squared, that's your 17.5. Doesn't hurt to label it on the picture, right? All of that divided by 2 and divided by b, which is the memory, and divided by c, which is the 15. Of course, the arc cosine at the end. How big is angle A?
86.2 degrees.
About 86.2 degrees. Now here we only have 2 sig figs in the angle, so we'll just go with the 2 there in that angle as well. Now again, a temptation would be for angle C to find it by just subtracting these two from 180. But the better way would be to actually write out that angle C equals
Arc cosine of a squared plus b squared minus c squared all over 2ab.
remembering that b is the memory, a is the 17.5. So we do 17.5 squared plus memory squared minus 15 squared. 2 divided by 17.5 divided by the recall and arc cosine. And how big is angle C?
59 degrees.
About 59, 58.78, but rounded 59 degrees. And then we can make sure they all add up to 180, and we have that way of checking at the end. Been a little while since we've done law of cosines. Really not since the third quarter exam have we had to do this. Questions on this? And Jamie's like, I'm so glad I'm exempt. And Quentin's like, stop rubbing it in, Jamie. He's like, I'm going to get it anyway. I don't care. You know, I got this. Solid. Yeah, you got this. All right, let's do another one. Let's take a triangle. Let's say we've got angle A, B, C. Suppose I know this is 5.25 feet. Suppose I know we've got a 41 degree angle here and a 72 degree angle here. Obviously, what do we need to find, class?
Angle B.
Angle B first, right? Because we got two angles already, and then also
Side C, side B.
side C and side B. Doesn't hurt to label these. And of course, this is A right here. Finding angle B, finding side AC or side B, and finding AB, also called side C. The angle is super easy to find. Unfortunately, the last time I didn't give you two angles. Here I did.
67 degrees.
How do we get 67 degrees?
Add the others, we can go subtract from 180.
Right. Now, unfortunately, we can't get away with not using the angle. What case do we have here?
Side, no.
Side
Side
angle,
angle,
angle.
Side angle, angle. Now, you could also say it's angle, side angle, now that we have this angle, but it started as a side angle, angle. Either way, anytime you know two angles, we're always going to use law of sines, which is really nice. We've got our 5.25 as A, over the sine of angle A, which is 72. B, we don't know, we're about to find it, over the sine of angle B, which I just found it to be 67. And then side C, which I don't know, over the sine of angle C, which is 41 degrees. We really could find either B or C. Let's just go with B, also called AC, so we're finding these in order. How do we find side B, class?
Cross multiply and divide.
Cross multiply and then divide, right? Start with these two, multiply, and then divide out what would have been multiplied by the B if we'd taken the time to write it. We were just too lazy. Again, making sure you're in degree mode. And what do we get?
5.08.
I ended up with a 5.081, blah, blah, blah. Rounded, good, we got the 3 sig figs, 5.08 feet. Does that make sense? It's about the same size as A, only a little smaller. Well, its angle's a little smaller than angle A. We should be expecting side C to be a lot smaller though, right? So this is clearly not drawn to scale, and that's okay. To find side C, remember, just ignore the existence of this and still cross multiply and divide out. And what do we get?
3.62.
Rounded 3.62 feet, which we should expect it to be a lot smaller because we got the smaller angle. It's a good way to check our answers here. Questions on law of sines. Considerably easier, right? But be able to work both of them. Questions at all on solving right triangles or solving oblique triangles? Solving triangles in general, of course, one of the biggest themes of trigonometry, which was a big part of the year. Any questions? All right, another thing that we worked on was using these trigonometric ratios. Given one, we should be able to find all the other trig ratios as well. By the way, we said we have 6 trig ratios. Of course, the big 3 are
Sine, cosine, tangent.
sine, cosine, tangent. We had 3 others. We had reciprocals, right? The reciprocal of the sine is
Cosecant.
the cosecant. It's been a while, hasn't it? The reciprocal of the cosine,
Secant.
secant, and the reciprocal of the tangent,
Cotangent.
the cotangent, right? So sine is whatever what?
Opposite over hypotenuse.
So therefore cosecant is
Hypotenuse over opposite.
cosine.
Adjacent over hypotenuse.
So secant,
Hypotenuse over adjacent.
tangent,
Opposite over adjacent.
so cotangent.
Adjacent over opposite.
Supposing we knew that the secant of beta is 13 to 5, and supposing I knew that the cotangent of beta is less than 0. What does less than 0 mean?
Negative.
Negative. How would trig ratios be negative? Well, depending on the quadrant in which the angle was formed. All acute angles have positive ratios. But as you move into the opposite quadrant, or alternate quadrant, second quadrant, third quadrant, fourth quadrant, remember, we had to use reference angles and reference triangles. And so we ended up with some negative lengths here and there. We had a 4-letter acronym. Do you remember the 4-letter acronym? Do we at least remember that after this class, all students take calculus? So what's our 4-letter acronym, class?
ASTC.
All students take calculus, ASTC. ACE meaning that in the first quadrant, class,
Positive.
all functions are positive. In the second quadrant,
Sine.
Sine.
sine and
Cosecant.
it's reciprocal cosecant, something in the next room just crashed. Third quadrant,
Tangent. Cotangent.
tangent, cotangent positive. In the fourth quadrant,
Cosine, secant, positive.
cosine and secant positive. So secant here is listed as being positive. Well, where would that happen?
1
And 4.
1 and 4. But cotangent is listed as being less than 0 or,
Negative.
where would cotangent be negative?
4.
4 or 2. So clearly we are in
Quadrant.
quadrant 4. So for my trig ratios, remember, in quadrant 4, the only ones that will be positive,
Cosine and secant.
cosine and secant. All the others end up being negative ratios when it's all said and done. Now, we already know, of course, one of the ratios.
Secant.
secant, so we can put in the 13 to 5, which means we also know
Cosine.
cosine without doing any math at all.
5 over 13.
5 to 13. In order to find the other ratios, though, we need to not know just what secant offers. Secant, again, is what over what?
Hypotenuse over adjacent.
Hypotenuse over adjacent, the reciprocal of the cosine. So the side we're missing, class, is the opposite. And to find it, we would simply use Pythagorean theorem. What is the length of the opposite leg in this particular triangle?
12.
So knowing that, we know the sine,
12 over 13.
negative 12 to 13, which means the cosecant,
13 over 12.
negative 13 to 12, and the tangent,
12 over 5.
negative 12 to 5, opposite over adjacent, so the cotangent,
5 over 12.
negative 5 to 12. All right, do we remember doing this? Do we want to practice one of these on our own, or do we feel pretty good about it? You're good. All right, basically, that's the first page of the exam. All right, what we've just gone over, similar problems, not those exact problems, of course, but similar problems. Again, Jamie, you're remembering this just for your own benefit, but you feel good about this for the exam. All right, excellent. And of course, you can certainly go back and re-watch video. Past years never had that opportunity, but we do. The next thing on the exam deals with trig identities. Open that front cover of your textbook if it's not ripped off already. Quentin's like, Jamie, I pay you to give me that front cover of the textbook.
Literally Friday.
Oh, Murphy's Law. Anything bad that can't happen will happen at the worst possible time. All right, now we didn't ever memorize the product to sum identities or the sum to product identities. So the top and bottom of the second column, we never did anything with those. We did memorize the rest of them. For your benefit, though, we're going to take off the double and half angle identities. All right, so that'll narrow it down. Cofunctions, remember, have to do with 90-degree difference, right? Negative angle identities, we have even and odd functions. Pythagorean, we worked on quotient, reciprocal, sum and difference, remember? Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. And then there was the tangent, all over 1 minus plus tangent, which, there's not a good way to remember that. Not cool, at least like the others. You're not going to have to use these necessarily, but you will have to be able to identify if they're correctly written or not. You're going to see a true-false section. And I'm going to write the identities, and I'm mean. Negative sign, switch the order on something, so you know them well enough to identify if I'm lying or not. That's basically how you have to be able to use the identities, all right? So kind of tuck that thought aside there. All right, the other next thing that we did, that's actually chapter 6. And then we had those. Chapter 7 was, so we kind of skipped over chapter 3, by the way. Chapter 3 was all radians. Chapter 3 was all about radians and stuff. I don't think there's any radians on here. No radians on here. Okay, so we'll spare you the radians. You just keep that calculator in degree mode. Chapter 4, recall, was the ASTC, a lot of ASTC there in chapter 4. Chapter 5 was graphing sine, cosine, tangent. You will not have that on this, okay? So graphing your trig functions won't be on here. We've got other graphing to do that's more recent that we have on the exam instead. Chapter 6, I said, was trig identities. Chapter 7, trig equations, where you're actually solving for a particular value. For instance, write this down. We might have something like 2 times the cosecant squared alpha minus 5 equals negative 1. Well, this is a conditional equation. It's only true for certain values of alpha, certain angles. That double the cosecant squared of that angle, or those angles, minus 5 would equal a negative 1. To solve, we said we solve it like a lot of other equations. We try to isolate the trig function instead of isolating x. So what would I need to do? Some different steps here to isolate.
Move 5 over as positive.
And when I do that, gives me 4, and then
Divided by 2.
to get
2.
2. And then
Take the square root.
take the square root of the cosecant squared and of the 2. Square root of cosecant squared, of course, just gives us cosecant alpha. And then when we take the square roots of 2,
Positive, negative.
and it's always good to put things in ratio form, so we'll put it over 1 just for our own benefit. Any questions on the algebra? That's not trig, that's just algebra. Are we good on that algebra step? Then the question became, well, when is cosecant or
hypotenuse over opposite.
square root 2 over 1. And you'll remember we had special triangles. Remember we had a special triangle with 45-degree angles. Call it 45, 45, 90, 1, 1 square root of 2. We had another special triangle, remember, the 30, little small one, 60, bigger one, 90, of course, the right angle. The little side 1 was across from the 30. The biggest side 2 was across from the 90, and across from the 60, square root of 3. And then we had another really annoying, and it wasn't even a triangle. We call it the 0, 90, 90 triangle. And of course we have the true 90 here, but up here we approached 90 degrees. Up here we approached 0. And if we approach 0 here, this side approaches 0. And these two sides approach the same, so we just said let's call them both 1. Okay, remember the special triangles. Okay, using that, when is hypotenuse square root of 2 an opposite one? 45 degrees. But because we have positive, negative, we need to account for all the times 45 would be in a positive quadrant or in a negative quadrant, or square root of 2 would be positive or negative. Well, that's all 4, right? Cosecant's positive in quadrants 1 and 2, and it's negative in quadrant. So I need the 45-degree reference angle for all 4 quadrants. So alpha here is going to equal
45, 315.
That's 1 and 4.
135.
135 when we subtract from 180.
225.
225 when we add to 180. All right, remember doing this? Let's do another one. Some of the trig equations really easy because there's only one trig function to isolate. Some a little bit more annoying. For instance, write this down. If we had 3 times the cosine of phi times the tangent squared phi equal to the cosine of phi. Well, here I've got multiple trig ratios. And we said back in chapter 7, if you've got multiple trig ratios, you need to set the equation equal to
0.
And
Factor.
set it equal to 0 and factor. So we resist the temptation, right, to divide out the cosine. We never do that. We set it equal to 0, but bring the cosines over as a negative to get 3 cosine phi, tangent squared phi, minus cosine phi, all equal to 0. And then
Change the tangent to, or
set it equal to 0 and factor.
pull out a cosine.
Pulling out that common factor. Again, that's just algebra. No trig in this yet at all. This has been algebra.
So 2, or still 3 tangent squared b minus 1 equals 0.
And then I've got 2 different factors. I got cosine and 3 tangent squared minus 1. What do I do now? I've set factor, and I've set it equal to 0.
Both equals 0.
Set each factor equal to 0. Well, here, of course, that's just cosine equals 0. Or we might say positive, negative 0 over 1. Remember, 0 is neither positive nor negative, so it could be considered both positive and negative. What about on the other thing?
Add 1, divide by 3, take square root.
So if I add the 1, that gives me 1. If I divide by 3, that gives me 1/3. And then you said take the square root, but thoughts?
Positive, negative. Well, you
You
can't
can't have
have a
square root
denominator.
Yeah, I mean, we could say this is positive negative 1 over the square root of 3, or we normally would say positive negative square root of 3 over 3. Now, if you're a unit circle line diagram person, this works great. I do think this works better if you're a triangle person, and Quentin, that's the case with you, right? You do the triangles a little bit more readily. You're going to be better off leaving 1 over the square root of 3, so you can see tangent is
1 over square.
opposite over adjacent, right? You can see the opposite, you can see the adjacent. Of course, cosine is
Adjacent over hypotenuse.
adjacent over hypotenuse. So we can see the adjacent, we can see the hypotenuse. Let's start with the cosine here. Adjacent 0, hypotenuse 1.
90.
That's this 90-degree angle up here. But positive negative means both 90s. Well, your positive 90 would be here. Negative 90 would be 270. So we can say that phi is both 90 degrees and 270 degrees. That's from the first. Then we come over here and say, okay, when is tangent 1 over the square root of 3?
opposite
30,
degrees.
30 degrees has an opposite of 1 and an adjacent of square root of 3. Again, in the unit circle, the square root of 3 over 3 is that little bit bigger than half line. So remember, we've got right at 30 degrees, the sine line's exactly half. The tangent line's just that little bit bigger than that, like 0.6-ish, which is your square root of 3 over 3. Again, unit circle or this, we get 30 degrees. But again, this positive negative tells me all the 30 degree angles. So phi is also
So it's 30, 3 30.